All right, 2.10, the last section in Chapter 2. Derivatives of log functions and log diff! I'm just reading what's on the page. Okay? All right, so here's a log, right? It's a hollowed out log. Maybe something you'd stumble over in the woods if you were texting while you were walking, right? Or reading while you were walking. If you draw a vertical line and a horizontal line that are the x and y axis at the base of this little stump that's sticking out, and you extend the vertical asymptote straight down, it becomes the L in the word log, and the curve of that branch ends up looking very similar to what the graph of the log function looks like. So what we're going to look at today is then how do I, if I want to figure out what the slope of that branch is that's sticking up right there at that moment, or how fast that little wooden branch is changing at that moment. That's exciting information, right? No hike through the woods is complete without having that information. We're going to need to know something about the derivative of a log function, right? So that's what we're going to be doing in this section. We're going to be learning how to take the derivative of logs. But first, because everyone loves to hate logs, we're going to review logs a little bit, okay? So here's the definition of a log function. If b is greater than 0, positive, but not 1. So between 0 and 1 and greater than 1, much like exponential base. And then if f of x is equal to b to the x, the one-to-one exponential function, it has an inverse function known as log base b. Okay, so the inverse of exponential base b is log base b. And this is what I call the conversion formula. It's an if and only if theorem. It's one of the ways you can go back and forth between exponential representations of data and equivalent log representations of the same data. So we can read this starting with an if and a then. That's what a postulate is. So we could say if b, the base, raised to the x power equals y, then log of the same base b of y is equal to x. Okay, so you can read it that way. You can also flip these two things around, and you can put the f at the bottom and the then at the top. So it works the other way. If log base b of y is equal to x, then b to the x power equals y. So y'all maybe learned in Algebra 2 how to go from logs to exponentials. You started with the base, and you went maybe around the world. I don't know if your teacher said that, right? So you go b to the x power equals y. All right, that's what you're doing. But I'm going to kind of back up from there. Because remember, we know how to write math equations and English equations. If we translate this, this says the log, remember the equal sign is the verb is, x. So this says the log is x. We'll look at it in exponential form. What is x? X is the what? The exponent. So there you go. By the transitive property then, if log is x and x is the exponent, then the log must be the what? Exponent. And that's what a log is. A log is nothing more than an exponent. But it's not an arbitrary exponent. It is the exponent to which you must raise the base of the log b to achieve the thing on the other side, or to achieve the argument y. Sorry. It is the exponent to which you must raise the base b to achieve your argument y. That's what a log is. And it helps us make big numbers small, make molehills out of mountains, or make small numbers big, like microscopic numbers, make them big enough, or make astronomical numbers small enough so that we can work with them. That's what logs do. They make it manageable. And they do that by working with powers of a certain base, like powers of e, powers of 10, and you can just look at the exponent on that number and use that as an indicator of the relative size of the number. Okay, that's what logs are. So we could read this like this. Log base 4 of 16 is equal to 2 because 4, the base of the log, raised to the exponent of 2th power equals the argument 16. So log base 4 of 16 is 2 because 4 to the 2nd power is 16. All right? So let's go ahead and evaluate these quickly. Are you done? Maybe not that quickly. We want to simplify this expression. Log base 2 of 8 is what? 3. All right? It's 3. It's equal to 3 if you want to call that equal to y. One of the ways you can solve logs is by converting it to exponential. So the log base is 2. and the log is y. It is the exponent to which we must raise the base of 2 to achieve the argument of 8. So 2 to what power is 8? 3. So that's one way to do it. You could do it like that. You could set it equal to a variable of your choice. I chose y here. Don't ask me why. And then convert it to exponential and solve. Okay, now you could solve it like this. If you didn't know that 2 to the y equals 8 when at y equals 3, you could do what I call getting the bases the same on both sides. Getting the bases the same. Because these functions are one-to-one, logs and exponentials are one-to-one, which we now know means pass the horizontal line test. If you have b to the x equals b to the y, that means that x has to equal y because they're one-to-one. So y has to equal 3. Now, if you knew that, you wouldn't even have to make an equation out of it. Look what else you could do. Let's just shrink all this down. You could write it like this. You could say log base 2, and then you could work on the argument. Try to write it as a power of 2. That's equal to 2 cubed. Right? So now you're saying 2 to what power is 2 cubed? Duh, 2 to the third power is 2 to the third. So this gives us a very important little property immediately that says log base b of b to the x power is what? X. That's a very important property. Because b to the x power equals b to the x power. How true that is. How true that is. Very important. All right, how about this one? Log base 3 of 1 over 81. Instead of setting it equal to x and converting it, let's try and solve it this way. Let's try and write the base as a power, the argument. Remember, the argument is the thing we're taking the log of. So I've used that term already a couple times. The thing we're taking the log of. Let's see if we can write the argument as a power of the base. So we have log base 3. Can we write 1 over 81 as a power of 3? Yeah. What is it? 3 to the negative 4th. Now, if you're not quite sure, do it in baby steps. 81 is 9 times 9. That's 3 times 3 times 3 times 3, or 3 to the 4th. And now if you want to bring it to the top, that's 3 to the negative 4th. So your answer should be negative 4. So again, reinforcing it, log base 3 of 1 over 81 is equal to negative 4 because the base 3 raised to that log exponent power of negative 4 gives you the argument of 1 over 81. All right, log base 16 of 4 simplifies to something. Anyone know? 1/2, good. Because 16, the base, to the 1/2 power equals 4. Or you can write it like this, log base 16 of 4. That's going to be the square root of 16, yes? So that's log base 16 of 16 to the 1/2 power. And so that must be 1/2. But if you don't like doing that, again, you could set it equal to x and then go around the world like your algebra teacher taught you. 16 to the x power equals 4. And now you just try to write the base as a power of the same thing. This is 4 to the first. So you can write that as 4 squared to the x power equals 4 to the first. And that's 4 to the 2x equals 4 to the first. And now since they both base 4, you could drop them and say that 2x equals 1 and x equals 1/2. So the reason that most students are disgusted with logs is because there's so many things to remember. But that's exactly what makes them so darn useful. Okay? So it's a love-hate relationship. I love to hate you, I hate to love you, but we need each other. We need logs. All right? Without logs, how will we make dugout canoes? Okay. Example 2. Sketch the graph of the log function log base b of x for the following. State the domain and range. Okay, so if the base is greater than 1, this is going to be just like exponential. It's going to be logarithmic growth. Logarithmic growth. So it's going to be a monotonic increasing function. Here's what it would look like. This is y equals log base b of x. They're going to have some common properties in this form. They're going to have vertical asymptotes, always on the y-axis at x equals 0, and they're always going to have x-intercepts at 1, 0, which means immediately log base b of 1 equals what? 0, right? Doesn't matter what the base is. And why is that true? Because if you convert it, b to the 0 power equals what? 1. as long as the base isn't 0. 0 to the 0 is indeterminate. We'll learn about that later. But we know the base can't be 0 because I said right here the base has to be bigger than 1. All right, so anything of that form, log base b of x where b is bigger than 1 is going to be logarithmic growth. Now, unlike exponentials where the bigger the base, the steeper the graph, the bigger the base for logs, the less steep the graph, the smaller it grows, or the slower it grows. So the domain would be the set of all x such that x is greater than 0. The range is going to be all real numbers all day long. So logarithmic growth, that means it's an increasing function. The derivatives are always positive over the domain. All right, then over here, if we look at a base between 0 and 1, just like if it were exponential, this is going to be logarithmic decay, which means it's going to be a decreasing function. So if you want to sketch this dude, it also has a vertical asymptote on the x or the y-axis at x equals 0. It also passes through the point 1, 0, because after all, log base b of 1 is 0. But now it's going to be a decreasing function like that. Logarithmic decay. All right, so here are some properties to recall from Algebra 2/Pre-Cal. When we say the natural log of x, that's the special name given when the base of the log is e, the natural base. The natural base of the log, when the base is the natural base, we get the natural log. Your calculator is pre-programmed in base e, ln. If you don't see a subscript, it's implied to be 10, the common base, or the scientific base. Those are the only two special logs that we have. And again, your calculator is pre-programmed to handle base 10. Every other base has to be explicitly stated by log, log, base of the number. And then the thing we're taking the log of is called the argument. And then here's a picture over here. Some logs become dugout canoes. Some dugout canoes don't get finished and become firewood. Okay? You ever built one of these things? They take a long time. Okay? But when you're done, you have yourself a nice dugout canoe. Example 3. Use the properties of limits to find the limit of each of the following. Okay. Limits. That's calculus, right? We're looking for the right end behavior. How are we going to do this without the graph? Just know? That's what you said? Memorize what logs do. Yeah. Remember, the limit can be, you could take it on the inside. This could be, let me start off. Let me put the natural log of the limit as x goes to infinity. You can actually bring it to the inside. So now just focus on the inside. What happens to x squared minus x as x goes to infinity? Remember, for this, you only need to look at the leading term. And you can kind of plug in an infinity. What's infinity squared? Infinity. So you can't say you can't replace this with infinity and say natural log of infinity, not per se, but you can figure out what that means. In fact, what you do write, though, is the limit now as x goes to infinity of the natural log of x. But it's kind of the same thing. This is what you could do in your head, and this is what you would have to write if you were showing work. But at any rate, what is the natural log of infinity? Or what happens to the graph of the natural log as we go out to the right? Yeah, it goes to infinity. Very, very slowly, right? So this one is infinity. Or, of course, dne, but infinity is a better answer. So that's the end behavior. That's pretty good. What about this one? The limit as x goes to 9 from the right-hand side. Well, again, you can either think about what the graph looks like. What does the x minus 9 do to this graph? It's on the inside, so it's going to be horizontal. It's going to move it right 9. So if the vertical asymptote used to be at y equals or x equals 0, now it's at x equals 9. And it looks like that because it's a base 2, it's growth. What would be the limit then as we approach 9 from the right-hand side? Negative infinity, right? Negative infinity. Or dne. Negative infinity is better. So that's how you do it with the graph. How could you do it otherwise? Well, using the properties of limits, remember, you could take the limit inside. So that's log base 2 of the limit as x goes to 9 from the right of x minus 9. And you could solve that one by direct substitution, right? When you plug in a 9, you get 9 minus 9, which is 0. Now remember, you can't say log base 2 of 0. even though that is equal to 0, because now you're turning it into a function value instead of a limit. So instead of doing that, we just let 0 be the new value that we're approaching, still from the right-hand side, on log base 2 of x. So you get the same answer. You still have to know that as you approach from the right-hand side, you're going down to infinity. It's exactly composition is what it is, yes. Now what if I change the base to 1/2 instead of 2? That would now be logarithmic decay, so as I approach now from the right side, it's going to go up to positive infinity. So that's why it's important to know if it's log growth or decay. All right, this one here, go ahead and figure that one out. Take like 20 seconds. Composition again, if you want. Anyone have an answer? These have been great multiple choice questions. If you bring the limit inside, like I did on the line below, now you're just focusing on the tangent part. You got to know what tangent looks like. So remember, this is what tangent looks like. It has vertical asymptotes every odd pi halves. So 1 pi halves, 3 pi halves, so on and so forth. Because we're approaching the vertical asymptote then from the left, here's pi halves right here, we're approaching from the left, we're going to infinity. So now this becomes the limit as x goes to infinity of log base 10 of x. And is that logarithmic growth or decay? That's all you really need to know at this point. It's growth, so it's going to be approaching infinity. If it were base 1/10, it would be going to negative infinity as you go out to the right. Logarithmic growth, logarithmic decay. All right, last one for this little section. Go ahead and knock this one out on your own as well. If you need to show the composition, show extra step, please do so. Be successful. Anybody have an answer? What'd you get? 0. You got 0? Anyone else get 0? 0 is the right answer. Very good. You plug in a 0 on the inside, and you get cosine of 0. Cosine of 0 is 1. So now that's the new value that we're approaching, still from the right-hand side on the next layer, which is log. Oops. I wrote log instead of limit. Stupid me. Okay. Log base 10, if you want to add that, of x. And so here we can use direct substitution. Log base 10 of 1, of course, is 0, because 10 to the 0 is 1. So there's the answer. So that's kind of now we're looking at a brand new function, but we're bringing it up to speed with everything we've talked about this year, limits included. All right, so example 4 makes a nice little pre-calc question right here. For g of x equals log of x squared minus 3x plus 2, find the domain of g. All right, so now, unless it's a piecewise function, there are 3 things that we need to try to prevent in terms of domain. Can't divide by 0, can't take square roots, fourth roots, even roots of negative numbers, and now we can only take logs of what type of numbers? Positive. Good. So whenever you're trying to find the domain of a log, you're going to take your argument, the thing you're taking the log of, and you're going to say it's strictly greater than 0. Strictly greater than 0, right? So for us, that's x squared minus 3x plus 2 strictly greater than 0. And remember, because that's a quadratic inequality, you can't solve that one algebraically. You either have to test intervals or know what the graph looks like, which is what we're going to do. You know that's a parabola that opens sideways or up or down? It opens up. Good. So if I can find the x-intercepts, I can sketch the graph quickly. So if I factor it with the inequality intact, it's x minus 2, x minus 1. Now what you cannot do is the following. You can't say x minus 2 is greater than 0 or x minus 1 is greater than 0. That's where it breaks down. But you can still keep it factored because that's the original quadratic. You're going to now graph it. There's 1. That's the first x-intercept, bless you. There's 2, bless you. There's the next x-intercept. I thought another sneeze was coming. And then it looks like this. And now we go to the inequality. I want to know exactly for what values of x is this thing strictly positive. Strictly positive means above the x-axis. So based on the x-intercepts, it's going to be everything strictly to the right of 2 and everything strictly to the left of 1. So that's your domain. The domain is the set of all x such that x is less than 1 or x is greater than 2. Remember from pre-cal, that's a disjoint interval. So you don't write it like this. That still has the alligators eating the correct number, but you reserve the compound inequality, as that one's called, for the less than or equal to case. If it's an or case, because it's two disjoint intervals, you need two separate inequalities. All right, so now, remember, this is not the graph of g of x. That's just the graph of the argument. We can now answer questions like this. What is the limit as x goes to 1 from the right-hand side? Does it exist? No. Remember, we said the domain is everything strictly to the left of 1 or to the right of 2. So the only numbers we can use to the left of 1 are the ones that are to the right of 2. If I'm approaching 1 from the right-hand side, that means just from the right of 1, there's no graph to even hop on to approach 1. So that one's D and E because there's no graph there, not because the y values don't exist or the limit of the y values doesn't exist. What would be the limit now as we approach 1 from the left? Well, think about this. As we approach 1 from the left on the inside here, we're on this parabola, and we're approaching 0, right? From where? From above. Yes, we're approaching the x-axis from above. So we're going to have positive inputs. What then would be the log of 0 as I approach 0 from the positive side of 0? In other words, what would be this answer? What would be the limit? What would be the limit as x approaches 0 from the positive side of 0 of log base 10 of x? Negative infinity. Good. Negative infinity, because there's a vertical asymptote. It's growth, so we're approaching negative infinity. So that's the answer to this one. Or D and E, but for a very different reason. All right, so now that you know that little trick, go ahead and figure out part 3, the limit as x goes to 2 from the right-hand side. Bless you. Bless you. Anybody got it? Same idea here. We know that we can live to the right of 2. If you hop on the graph of the parabola, as you approach 2 from the right-hand side of 2, you're approaching 0 from the positive side of 0. So that again becomes the limit as x approaches 0 from the positive side of 0 of log of x, which is still negative infinity. Still negative infinity. Notice we're doing all of this without the graph. We don't really know what the graph looks like. All we have is the graph of the parabola on the inside. All right, what would be the limit as x goes to infinity? Yeah, these are a little bit easier because now you can almost just use direct substitution. If this were a multiple choice question, on the inside, who cares about those terms? Plug in an infinity there. Infinity squared is infinity, and log of infinity is infinity. Yeah. So that would be the right-hand behavior. And then the limit as x goes to negative infinity, same thing. What's negative infinity squared? Infinity. So now it's log of infinity, which is infinity. So it's important that it is base 10 still, because if that had been the logarithmic decay, those would both be negative infinity. All right, very cool. What would the answers to all the above be if we were looking at, there's that question I just kind of alluded to. What if the base were 1/10 instead of 10? Yeah, you'd flip all the signs, essentially. These would both be negative infinity. Would these flip too at the vertical asymptote? They would. Yeah, they would. So all the infinity signs would be opposite signs. All of the infinities on 2, 3, or B2, B3, and C1, C2. That sounds like an Android catalog, like from Star Wars. Not like from phones. Anyway, yeah, we got the new B2, 3 in today. Who were the little guys that had C3PO? The little guys, they weren't the Jesuits. They were the Jesuits. Yeah. Francis Loyola in the group there. Okay. The Jawa. That's right. The Jawa. All right. Properties of logarithms. Properties of logarithms. Logarithms. Logs make molehills out of mountains. Okay. Again. So they turn products into sums. They turn quotients into differences. And they turn exponentiation into multiplication. So they bring everything down one rung on the operational ladder. So for us, that just means if I have the log of a product, I'm going to add the logs together. The log of a difference, or of a quotient, is the difference of the logs. They each get their old logs. And the log of exponentiation becomes multiplication. It linearizes, essentially, exponents. And then we have this other column over here. Because log base b and exponential base b are inverses, when you compose them back to back, they're commutative, you get the same thing you start with. So for this one here, if you start with x, if you b it, exponentiate it base b, and then turn around and log that base b, you're right back where you started with x. Or if you log it base b first and then exponentiate it, you're right back where you started with plain old x. So this kind of preserves the inverse nature of log base b and exponential base b. You can compose them in any order and get the same answer. And then as I showed you earlier with the get the base is the same method, it not only works with exponentials, it works with logs because logs are also one-to-one. So if you can get the logs to be the same on both sides, log base b of something equals log base b of something, you can drop the logs and just equate the two arguments. All right, so we're still not ready for full-fledged calculus. Use the properties of logs to solve the following equations. So back to Algebra 2/pre-cal. All right. Trying to find the values of x that when I plug it in give me values of 3. Trial and error? Anyone? No? What should we do? It was always a pretty good thing to do to convert it to exponential. That way you got rid of the logs. So there's two ways to do that. You can put the base 10 there. It's kind of nice to see the base. And then you can go around the world if you like to travel. 10 to the third power is equal to x plus 1. That's one way to do it. That's fine. But I'm going to do it a different way. And I'm going to get the same result. We are logging it right now base 10. What is the inverse of logging it base 10? Exponentiating it base 10. So that's what we're going to do. We're going to exponentiate both sides base 10. And that's how you can show it. The left side now becomes the exponent on the base 10, and the right side of 3 now becomes the exponent on base 10. And now we can use this property right here that we just learned right here. B to the log base b of x is just x. So what happens to the left side? What is 10 to the log base 10 of x plus 1? X plus 1. We don't even need parentheses. And over here we get 10 to the third. So you get the same thing. So instead of going around the world, exponentiate both sides. And now you end up with x equals 1,000 minus 1, which is 999. There we go. Does that number make anyone nervous? Like Satan doing a headstand? No. All right. Okay. E to the 3 minus x equals 14. Yeah, I got to solve for x. Yeah, we've already seen something like this. I need to get the x out of the exponent now. We typically use the natural log, and it's base e, so that's the natural choice, of course. So you get the natural log of e to the blob equals the natural log of 14. So we're taking the natural log of both sides. And, of course, now the natural log of e to the blob is just the blob. That's using this other one right here. Log base b of b to the x is just x. And that equals the natural log of 14. So if we solve algebraically, we get x equals 3 minus the natural log of 14. And there's a fine and dandy answer. But let's see what we could do with that. Let's play with the log. We can call the natural log of 14 the natural log of 7 times 2. Yes? And so that becomes 3 minus the quantity natural log of 7 plus the natural log of 2, which now if I distribute, I get 3 minus the natural log of 7 minus the natural log of 2. So what that does is that you can see the power of logs right away. It takes a 14, which is a huge number, right, and turns it into two smaller numbers, 7 and 2. So I might mess around with answer choices like that. College Board might mess around with final answer choices. Just be ready to play with logs when you get to your final answer, just to consider what other things could be done. All right, part C. Now I have two logs, both with variables in their arguments. In order to solve for x, I need to first what we call condensing. So that would be starting with something that looks like the right side, condensing it to make it look like the left side. The left side is the condensed version. The right side is the expanded version. And they work both ways. So for this, since they're both logs, I'll pull one log out. The term that was positive is going to be multiplied in the numerator. The term that was negative is going to have its argument multiplied in the denominator. And then that, of course, equals 1. So now that you've got it down to a single log, now you can either do around the world or exponentiate both sides, which I'll do. What is the base on the natural log? E. So when you exponentiate both sides, you can just literally kind of stick the e down there to the bottom left. So now the left side and right side become exponents. And on the left, what is e to the natural log of blob? Blob. And on this side, we get e to the first, which is e. And now we don't have a log equation anymore. We have a rational equation. How do we solve this? If I put that over 1, would that help? We have a proportion now. Cross, multiply would work. Yeah. X times 1 is x equals e times the quantity x minus 1 is e times x minus 1. If you distribute now, you get x equals x, the word x, or e times x, I should say, minus e. And now I got to get my x terms together. So if I subtract e times x, I get x minus e times x equals negative e. Is that going to help me? Well, yes, I could factor out the x because they're like terms, but they have unlike coefficients. So if we factor out the x, what are we left with? 1 minus e. Not 0 minus e, but 1 minus e. That's a common mistake. And then we're almost there. We'll divide through, and we get negative e over 1 minus e. But now in the spirit of Rachel's challenge, we have 3 terms. 2 of them are negative. The majority of them are negative. So what would we do to fix that? Yeah, essentially change the signs on all the terms by multiplying by negative 1 over negative 1. So now we get e over e minus 1. And that's just a better looking answer. All right, the only calculus we've done so far is the limits. This is good old-fashioned pre-cal. And even limits we did in pre-cal. All right, this one here. You do have logs on all three sides, but you don't have to get all the logs on one side. If you can get a condensed log on each side, then you can set the arguments equal to each other. So let's go ahead and condense the left side. They're both log base 10, and both of the terms are positive. You see that? So that means that their arguments are going to get what multiplied? Multiplied. Yeah, very good. And that equals log of 6 over here. Now, because you have log of something equals log of something and they're the same base, now you can just equate the arguments. So x squared plus x, when you expand, is equal to 6. Now that's the same thing as actually exponentiating both sides base 10. So if you'd still like to do that, that's kind of fun. 10 to the log base 10 of blob is blob. 10 to the log base 10 of 6 is 6. How would we solve this quadratic equation now? Yeah, bring the 6 across and factor. Excellent. So we get x squared plus x minus 6 equals 0. X minus 2, x plus 3 equals 0. You get x equals 2 and x equals negative 3. Are they both good? Yeah, we haven't really been checking here, but remember that you can only take logs of positive numbers. Did we start with a quadratic anywhere in our original problem? No, we had linear arguments. We turned it into a quadratic in the effort of helping us solve it. So whenever you take something of a certain degree and you make it bigger on the way to solving, by either squaring both sides or cubing both sides or just condensing, you have to check for extraneous solutions. Because quadratics can have two solutions where linears can only have one. One of them may not work. So when in doubt, try it out on your logs. When you plug a 2 in, you get log of 2 and log of 3. Those are both positive arguments. When you plug in a negative 3, you get negative 3 and negative 2. It doesn't work in either one of them. If it worked in one but not the other, it wouldn't work in the whole thing. So x equals negative 3 doesn't work. It's extraneous. Let's go back and check our other logs. If I plug in an e over e minus 1, will it work? Yeah, that's a positive number. We'll just say it works. And, of course, up here, if you plug in 999, 99 plus 1 works. Okay. So it's really only at risk when you make a quadratic out of something that started linear, or cubic out of something that's linear. All right, enough of the non-calculus review. It's time to BOTC. Get out the good stuff. Bust out the calculus, right? Which is what your parents say when you have guests coming over, right? Oh, let's get out the good stuff. Bust out the calculus. Let's impress them. Putting out the china. Been married for 20 years. Never used the china that we got when we got married. Still sitting in the cabinet at the house. Looks pretty when you walk by it. Never used it. Or the flatware that we got with it, right? It's always too nice. Too nice for us. So the china decorates the cabinet through the glass windows, and the flatware decorates the drawer with the drawer closed. Yeah. Right. Can we use it? No, we can't use that. It's too nice. Okay. Right. Those expensive decorations. Example 6. Example 6. If y equals the natural log of x. Yeah, if. Okay, we'll let it. Derive dy dx, the derivative of the natural log of x. Is this a trick question? Remember when we were trying to figure out what the derivative of inverse sine of x was? And we were like, okay, what is it? We didn't know what it was, so we can't do it. In other words, if you take the derivative of both sides, you get dy dx equals the derivative with respect to x of the natural log of x. And now you're stuck because you don't know what the right side becomes. What do we do in the arc sine case back in the day? You're going to maybe go back and look at it? We had y equals arc sine of x. And you remember what we said? We said, you know what? We don't know the derivative of arc sine of x, but we do know the derivative of sine of x. So you remember what we did? We took the sine of both sides and we had sine of y equals x, which gave us something to work with, and it wasn't any longer solved for y explicitly, but we do have that other method of differentiating, right, implicitly. So that's kind of the same little trick we're going to do here. We're going to convert this to its equivalent exponential form by exponentiating both sides base e. And you get e to the y power equals e to the natural log of x, which of course is what? X. Do we know how to take the derivative of e? Yeah. When we were born, we knew how to take the derivative of e. It was that easy, right? Now we're going to take the derivative of both sides with respect to x. And this is implicit differentiation. Okay, here we go. What's the derivative of e to the y power? E to the y power times the chain rule, dy dx. Sweet. And on the right side, the derivative of x is 1. All right, now we solve for dy dx. And we get 1 over e to the y power. Yay! We discovered that the derivative of the natural log of x is 1 over e to the y. And I'm no more satisfied with that answer than I was with the arc sine's derivative. Remember, it was in terms of y as well. So we had to draw a little picture and get the triangle. We don't have to draw a picture here unless you want to. What is e to the y equal to? It's equal to x. OMG. Is that oh my gosh or goodness? Oh my gosh? Okay. When you say oh my goodness, it sounds like your Little Red Riding Hood, doesn't it? Oh my goodness. What big eyes you have. I know the story. You're going to want to memorize that, so you don't have to derive it every time. All right? Memorize it. Let's write it right here. The derivative with respect to x of the natural log of x is 1 over x. Now, what's the domain of 1 over x? Everything except 0, right? What's the domain of the natural log? Everything greater than 0. So because we're starting with the natural log of x, the derivative of the natural log of x is 1 over x for all x greater than 0. In other words, you're only going to see one branch of that reciprocal function in quadrant 1. Okay? But it works. It works. Let's look at it graphically. Natural log of x, let's sketch that right here in blue. And we'll go ahead and in green, we'll put the derivative function, which is that one branch of 1 over x. And we're claiming that the green y values represent the slopes of the blue graph. Let's see why. If you take out your meter stick, right there, as I get close to the x-axis, the slope of the natural log function is a very big positive number because the slope is very steep in the positive direction. So at that x value, it's going to be a really big y value, way up there, about where my hand is. As I go to the right now, my slope is still positive, but it's smaller. And if you just follow the slopes on the natural log, your slopes are flattening out, approaching what? 0. Now, will the slopes of the natural log of x ever equal 0? No, because the natural log of x does go to infinity just by a slower and slower rate. It never reaches a horizontal tangent line on natural log of x, which is why the y values only approach 0 on the derivative. So it's pretty cool. Pretty cool. So we never get to see this other branch. We never get to see the other branch of 1 over x if we start with the natural log of x. That's kind of unfortunate because there's some good y values on that side, aren't there? They're negative, albeit negative, but they're still pretty good y values. I wonder if there's a way to incorporate them. Example 7. All right. It's nice to set up your own segues. F of x equals the natural log of the absolute value of x. We're going to take a look at that function. What would that graph look like? We just studied this transformation today and yesterday in pre-cal, and they're like, I don't get it. But they will eventually. They're young. You know that this transformation does what? By definition, it's an even function, right? Because you plug in a negative x and a positive x, you get the same output. So remember that transformation. It said if x is positive, the absolute value of a positive x is just the same thing. So you're going to leave quadrants 1 and 4 alone where x is positive, and then you're going to take the graph in quadrants 1 and 4, get rid of any graph that might have lived in quadrant 2 and 3, and then reflect the graph from 1 and 4 over into the other quadrant. That's what the graph of the natural log of the absolute value of x would look like. Okay? So that allows you to now include negative x values because you're taking the absolute value of them before they ever get to the log function, which by then they have to be positive. So now let's see, what is the derivative of this left branch of the natural log of the absolute value of x function? Well, notice it's monotonic decreasing to the left of the y-axis. So the derivative should be negative. As we come in, we're coming from like a pretty small magnitude negative number to the slopes are getting more and more negative, approaching negative infinity, which would be the vertical line. The green branch of 1 over x in quadrant 3 does a beautiful job of representing the slopes of the second branch of the natural log of the absolute value of x. So that is indicating to us that the derivative with respect to x of the natural log of the absolute value of x is what? Still 1 over x. The only difference is we've expanded our domain now to be able to use the full domain of the derivative 1 over x. So that's kind of cool. It is true. When you take the derivative of the natural log of x or the derivative of the natural log of the absolute value of x, the absolute values just go away. Okay? We're going to verify that algebraically right now because we just saw the trend graphically. If we decompose the natural log of the absolute value of x into two pieces, if x is positive, that is greater than 0, the natural log of the absolute value of x is just the natural log of x, right? If that x in the absolute values is less than 0, I got to manually make it positive in my little piecewise program before it gets to the log, so I'm going to take the opposite of it, right? Now let's take the derivative of the natural log of x, absolute value of, using the piecewise pieces. Oops. All right, so for the top piece, when x is greater than 0, what's the derivative of ln of x? 1 over x. Sweet. And when x is less than 0, now we have the what rule? It's not natural log of x, it's natural log of blob. So that's the chain rule. What's the derivative of the natural log of blob, do you think? 1 over the blob times the chain rule, the derivative of the blob. What's the derivative of negative x? Negative 1. Oh my goodness. What big teeth you have. The better to eat you with. Actually, he should have said the better with which to eat you. Right? We're devouring this problem. What do we get? Because we have a negative times a negative, the bottom piece becomes positive. And we're left with a piecewise function? Is that still a piecewise function? That'd be a silly piecewise function, right? If x is bigger than 0, call it 5. If x is less than 0, call it 5. You mean call it 5 everywhere? No, except at 0. So we could just say it's 1 over x. And now we don't even have to say when x isn't 0 because it's inherently programmed into the problem, right? X can't be 0. X can't be 0. You get undefined. So there is the algebraic proof that the derivative of the natural log of the absolute value of the argument is the same as it would be if it were not there. All right, so memorize. The derivative of the natural log of x? 1 over x. Very good. The derivative of the natural log of the absolute value of x? 1 over x. Where did the absolute values go? I always get asked that. Where did the absolute values go? Away. They went away. And then here's the chain rule built in. 1 over blob times blob prime.
Come check it out. Please rise for the Pledge of Allegiance.
All right, we'll stop right there for today.